Hello. So yes, thank you. Yeah, as the title suggests, I'm not going to talk about cases, but about impredicativity. And I know this one. I assume you know what impredicativity is. So just why do I care? I work on a programming language I call Typer, which is in a kind of ML Haskell family, but with dependent types and macros. And I use it as a kind of low-level target language for a language workbench, let's say. And I ended up using impredicativity in a few places, like for first-class modules encoded as tuples, or for a type-preserving closure conversion algorithm, and for various things that are kind of system F style encodings. So in most of those, I could live without impredicativity, except maybe for closure conversion, where really I have no idea how to do it otherwise, nor how to do it with known forms of impredicativity. Okay, so what do I mean by forms of impredicativity? Well, in type theory, I know of the following forms of impredicativity. The first is a kind of prop universe, like we have in Coq and Lean, etc., that we all know and either hate or love. And then there's kind of resizing axioms, like the propositional resizing. And then, of course, there's a very popular type in type, which is popular on one side, but not so popular on the other because it's unsound. And so we'd rather not go there. And what I'm proposing here is what I call impredicative universe polymorphism, which basically says, so like I show in the rule here, if we have a type tau, which lives in a universe U, which is an algebraic universe level with presumably some variable L that might appear in there, I can quantify over L, and then the resulting type is not going to be in some kind of type omega, but instead in the infimum, the lowest level possible type, where I replace L with 0, which is very optimistic, obviously. So the plan is I'm going to talk about, how did I come up with this crazy idea? Why it might make sense? And then some kind of limits of, where it becomes really crazy. And also how strong it is at the very least. And also some encouraging signs that maybe it's actually not unsound. So I first came up with this, or bumped into this idea when working with church-style encodings of data types. So when trying to encode data types as closures. As we know, this kind of encoding suffers from the fact that it doesn't have any induction principle, though there are some solutions now out there for that, and also suffers from a lack of strong elimination. Well, there kind of is some kind of solutions for that, but they're very limited. As soon as you have a hierarchy of universes, there are actually no solutions at all provided for that. But actually, for strong elimination with universes, you could just use, for the list type, you could use disk encoding where you parameterize over the level L of your elimination type, and then you can eliminate to any universe level you want. So it's very easy. Of course, the problem is then if you do that, what level are your lists? Like in which universe do your lists live? And if you follow the predicative principles like Agda will say, oh yeah, you can define that, but it's going to live in type universe omega, which makes it inconvenient to work with. But parametricity tells us that this type really is the type of list. There are no funny values in there. And so it should be safe to actually make it live in type level U, where U is the universe level of your type tau. And so the impredicative universe polymorphism rule that I suggest does actually put you not in type level U, but it puts this type in the type level, the maximum of U and 1. Not exactly as U, but it's good enough. You can definitely work with it. Basically, it's the same as U as long as you make sure you have a kind of, you use type level 0 as a kind of basement universe you never go to. And actually, the same shows up when you do the encoding in the other direction, where you try to encode closures as inductive types or just tuples in this case. So I show here 2 examples of what is closure conversion, where you turn a function which may have 3 variables into a pair of the captured environment and a piece of closed code. And when you do this conversion, the captured environment becomes exposed, becomes visible. And so your types, which originally may be the same, become different unless you're careful to actually hide the type of your environment. So you need to use types which take this shape, where you say that there exists a type T, which is the type of your environment, and then you have a pair of an object of type T and the closed function of type, T cross N, so that's the environment and your integer, arrow integer. And this kind of encoding works great in System F. We're very happy with this in kind of simpler languages. But as soon as you have type dependencies and universes, then things become more and more complicated. So if you have universe levels, then your existential on T has to say in which universe level this T lives, and the universe level in which T lives depends on the content of your environment, or in your captured environment. So again, different closures which originally had the same type will actually live in potentially different universes, and of course we don't want that if we want our closure conversion to be type preserving. So we need to hide the universe level. So again, we introduce another existential quantifier. So now the type of our closures will be there exists a level L, and then there exists a type T in this universe level L, and then our pairs of a T and the closed and this environment of type T and the closed code. So again, predicative principles tell us that this is fine. It just has to live in type level omega, and that would be safe, but that would be unusable in terms of proving that our closure conversion is type preserving. And again, parametricity tells us that this type actually is equivalent to the type just int arrow int. There are no funny values in there, so it should be safe to make it live in type level 0. And so our impredicative universe polymorphism rule actually, again, doesn't actually quite put it in type level 0, but it does put it in type level 1, which again is good enough as long as you keep your basement universe 0 empty. Okay, so that's the reason why maybe this is not completely crazy, but what if we push this even further and say, well, let's use this rule not just for existentials and for all quantifiers, but we really like it. We'll try to use it also for some types. Well, there definitely it breaks down, because then you can very easily define a lower and a raise functions, where your lower function takes any value in any universe, puts it in type level 1, and then raise extracts it back out, and then you just doing basically type in type just in a convoluted way. So it's definitely not going to work well. This actually suggests that the impredicative universe polymorphism is probably incompatible in general with first-class universe levels. Another way to look at the strength of that kind of rule is that we can actually encode system F into this system very easily, and so it's at least as strong as system F. I also then started to think that, it probably is a crazy idea, so I should be able to just take an existing paradox and just encode it into it and show that it's inconsistent. And so I tried to define, or you can try to define an ordering of an ordering. So this just shows you, where those things break down. So when you define an ordering over a carrier set in type level universe U, and then with some kind of lesser relation, and then some set of constraints on it. The inconsistency comes in when you try to instantiate sets with ordering itself, which with predicativity you can't do, because the type ordering lives in a higher universe than you. But here we have this impredicative universe polymorphism, which might let us lower the type ordering. So how do we do that? Well, we can do it with an existential quantifier and say, well, that type, if you quantify over the level L for your carrier set, then the type ordering 1 via this IUP rule lives in type level 1. So yes, we can instantiate sets to ordering. And so we may actually be able to prove this paradox, which I'm never sure whether I want to or whether I want not to. But in any case, if we try to do that, at least I was unable to do it because this existential quantification is weak, right? You cannot eliminate anything that depends on L, or you cannot to anything that depends on L, or to anything that depends on sets. And so basically you can't extract anything out of the box. It stays as a black box. And I was unable to define any kind of relation between orderings. So that's how how it fails with existentials. So I tried with universal quantification instead, and there again, the type ordering is brought down to universe level 2, and so potentially we could instantiate or put an ordering 2 into this set parameter. But now we're facing another problem because we need to define a function from a type level L to something that when L is 1, you want to put ordering 2 in there. And when L is 0, then you need to put something of type level 0 instead. But L is a second-class citizen. We can't do case analysis on universe levels. And so I don't know how to define such a function. It seems impossible in this situation. So that's where things break down in this case. So in conclusion, we have church encodings and closure converting encodings that suggest that this rule might actually make sense. And of course, some cases which show that we definitely don't want to go too far in this direction. We have shown that it's at least as strong as system F. And we have so far failed to encode known paradoxes into it. So there might be some hope that it might be consistent. I don't know. It's really a big question, and if anybody has an idea of how to show either that it's consistent or inconsistent, or maybe for subsets of it, I would love to hear about it. Thank you.